Welcome back. So now that you've read a little bit from the Mighty Atom reading, which is from my absolute favorite book about science, A Brief History of Nearly Everything by Bill Bryson, let's go through and let's just add a little bit of understanding to our understanding of atoms. Okay, so we started with that first section, just about like, what do we know about atoms? So atoms are kind of wild. And remember, I said that like a lot of what we're gonna talk about when we talk about atoms and subatomic particles is gonna make very little sense. If you think that you understood it, you might be wrong because it's super weird. Okay, so atoms are, number one, making up everything. Atoms make up all of the universe, kind of, right? Because we already know, or we will know, or we already know about dark matter and dark energy. So it turns out actually most of the universe is made up of stuff that's not atoms. But for what we understand, atoms make up everything. All of the stuff on the Earth and in the sun and throughout the universe are made up of atoms. Atoms are really, really, really abundant. So in a sugar cube, something that's like yay big, itty bitty, there are 45 with 18 zeros after it atoms. That's a lot of atoms. I think they phrased it as 45 billion billion, but that would be like million, billion, trillion, quadrillion, quintillion, 45 quintillion, I don't know, a bunch of atoms. Atoms are really, 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 really small. So small that we cannot see them even with the best microscopes. Obviously, if we're going to get 45 quintillion atoms inside of a sugar cube, they got to be itty bitty. And the atoms are around forever. Based off of the conservation of matter, matter is never created nor destroyed. So the atoms that exist have always existed on the Earth. So the atoms inside your body were at one point inside of a dinosaur. They were at one point inside of a lot of other people. The whole circle of life. Oof, that was a rough Lion King rendition right there. Okay, so that was section one. Then we skipped a little bit, and then we started talking about different models of the atom. So it talked about a variety of historical ways that we understood the atom. So first, it talked about a model where the atom was like a current bun. That's a very British reference. So the American reference would probably be like, it's a chocolate chip cookie. Currents are like raisins. A bun is like a morning bun, muffin, scone type of thing. So I would consider it like a chocolate chip cookie where there's a whole bunch of positive batter, right? And so they had this dense mass of positiveness. That would be the batter of the chocolate chip cookie, the cookie part. And then there's these little negative particles scattered all throughout it. And those would be like the chocolate chips or the currants in the currant bun. So this is kind of like what that would look like down here, where you have this like big positive mass where all the stuff being positive and then little negative nuggets scattered throughout. Turns out that is not what an atom actually looks like. So that is not a valid model anymore. We gained more evidence that said, actually, the positiveness isn't all in one place or isn't scattered all throughout. It's kind of in one centralized location. And we'll talk about that evidence. Then a second model that was come up with was that atoms maybe are like cubes. They're like the shape of a die or like a little box so that they can be easily stackable so that there's no space between them. If we're going to get 45 billion of them into this tiny little sugar cube, they got to be super stackable with no space between. But no, that actually isn't really the way that we think of them now either, right? So now we have a model of atoms where atoms are made up of a small, dense nucleus, so a center point that's super duper dense, with tons of empty space for electrons outside of it. So if we did like a blown up huge model, it would be like our entire basketball gym is emptiness, a vacuum with nothing there. And then all of the mass of everything in the gym is in a single little fly that's somewhere in the middle of the gym. And then the electrons are just zipping in and out around somewhere in the vacuum of the gym. Okay, so this is our current understanding and our current model of what an atom kind of exists as, is that most of it is nothingness. It's emptiness where electrons can pop in and out. So the electron cloud makes up the huge, vast majority of the volume of the atom. And all of the mass is in this tiny itty bitty particle in the middle. Okay, so how did we come up with that idea? They referenced Rutherford's gold foil experiment. I really like Rutherford because he just worked super hard. If you read that section about Rutherford, he wasn't especially bright. Sometimes he got a little bit lost, but he was a really hard worker, and that's how good science happens, is people work really hard and they persevere on difficult problems. That's one of the things that we kind of believe in STEM Marin, that we can do hard things if we try hard and persevere on them. So, and I also like Rutherford because he grew up in New Zealand, and that's where my family's from. So I'm a big fan of Ernest Rutherford generally, Ernest Rutherford. Okay, so he did this gold foil experiment. So what he did, he took a piece of gold and he flattened it down into the thinnest possible foil that he could make. So like an atom or 2 atoms thick. And gold is good for that because it's really malleable. You can shape it and flatten it pretty easily. So he made this super thin piece of gold foil right here. And then he put that gold foil inside of a chamber where he could kind of like identify any particles that hit the outside of the chamber. Then he fired alpha particles at this gold foil. So he shot alpha particles, and alpha particles are just 2 protons, so and 2 neutrons. So it's the nucleus of a helium atom. So he took nuclei of helium atoms, which we call alpha particles, and he fired them at this piece of gold foil. So what would we expect? We would expect that either the alpha particles should go straight through, right? Or if they hit the wall, they should bounce straight back, right? If the gold foil is solid, then the alpha particles should bounce back. If the gold foil, or if the alpha particles can create a hole in the gold foil, then they would go straight through and everything would hit on the other side. So 99.9999% of the time, like almost all the time, the alpha particles did go straight through. So we saw like this point right on the far side from where the alpha particles were being shot lit up. It was like, yep, alpha particle, alpha particle, alpha particle, alpha particle, like tons and tons and tons of action right on that point. But every once in a while, that 0.0001% of the time, we would see a little flash out on the side. So like a little flash out here, or a little flash out here, or a little flash down here. And it wasn't always in one location. It wasn't bouncing straight back. It was being like mildly deflected or just off by a tiny little bit. So what did that tell us? Well, it tells us that most of the atom, most of this gold foil sheet that's made up of 1 or 2 atoms thick, must be totally empty because these nuclei, these alpha particles, just went straight through the middle. But there must be something in there that is really, really tiny because it's only happening 0.00001% of the time, that's actually like dense and heavy enough to bounce the alpha particles away. And so that's the thing that we think is the nucleus, right? That's why we believe there's a tiny dense nucleus in the middle or somewhere in the center of the atom, because there's something in here that is strong enough and inert enough, like inertia staying in one place, that it can bounce the alpha particles, the 2 protons and 2 neutrons, back away every once in a while, if the alpha particle happens to hit it, or if it happens to glance off the side of it. That's why I would get like a bend and push. All right. So that's kind of like our current model of what an atom looks like. And that's the gold foil experiment is this classic experiment that comes up over and over because it kind of defined the evidence that makes us think there must be a nucleus with a ton of empty space. All right. So what does an atom actually look like? What is it? Short answer is we're not totally sure. We think there's, a center and then a bunch of stuff that is uncertain. All right. Then we talk a little bit about electrons. And electrons are kind of mind-bending. I think there was one piece in there where they were talking about how, like, if you want to touch something, if you touch the desk right now, go ahead, push down on the desk. Is your hand actually touching the desk? No, because two atoms can never actually touch each other. Because their electrons are just repelling each other really, really closely. So if two atoms could touch each other or move through each other, then you could put your hand down and your hand would just kind of like split through the desk. It would just like, or let's say like this, straight through the desk. But what's really happening is the electrons in the desk are holding your hand, the electrons in your hand, just barely above the surface. Now, it's close enough that on the macroscopic level, your nerves in your hand can feel the desk. But on a microscopic level, on a subatomic level, those electrons are not physically touching. Okay, so then we introduce this idea of wave-particle duality. So wave-particle duality. This is one that I had such a difficult time with. And we use wave-particle duality for electrons and also for light, because light is made up of this particle called a photon, but it's also represented by wavelengths. So the wave-particle duality, I just could not get my head around. And so I went, this is not why I went, but my roommate in college was an optical engineer. So he studied light and lasers, and he went to Harvard to do his PhD in applied physics. So when he got married, he had his wedding out at this little farm in Vermont. So I flew out to the East Coast for the very first time. And we were out there at his wedding, and there were a bunch of scientists that he worked with, people in his lab. So I was talking to one of them and about this like concept of wave particle duality. And I was like, it doesn't make any sense because a particle would have mass, right? But light doesn't have any mass. So how could light be a particle? And she told me, like, no, you're thinking about this wrong. The light or the electron is not a particle, and it is not a wave. It's sometimes easier to explain what it's doing as a wave, and sometimes it's easier to explain what it's doing as a particle. But electrons and light, photons, just are what they are. Light is light. Electrons are electrons. Now, when we perceive them, because it's on such a micro level, when humans think about them, sometimes we use a model of a wave, and sometimes we use a model of a particle. But the light behaves like in different ways depending on how we're thinking about it. So the same way that like I am a teacher as a person. Sometimes when I'm teaching, I behave in the way that a teacher would behave. Other times I'm a father, and then I behave in a different way. Other times I'm a husband. The way that I behave around my wife is a little bit different than the way that I behave when I'm in a classroom. Other times I am playing sports and I'm an athlete. And the way that I behave on a soccer field is going to be really different than the way that I might behave right in front of my wife. So there's this like different models work differently in different circumstances. So it's not that the electron or the light changes itself. It's that we have two different models of thinking and explaining what it's doing. So this wave particle duality is just that both models work. And sometimes I want to use the wave model, and sometimes I want to use the particle model. And the models are just ways of thinking about it. Okay, so electrons and light can be represented by two models, one for wave behavior and one for particle behavior. Both models are correct for different behaviors and different circumstances. So you can switch back and forth between the models, between the ways of thinking. And so we say that electrons and light have wave-particle duality. And then depending on what it's doing, we might switch which model we're using. Okay. With that, I would encourage you to take a look at, actually, I'll show you the video in just a second. We're going to watch a video about wave-particle duality. And then the other thing that we're going to start looking at is what are we actually doing in terms of research now? So with atomic research in physics, a lot of what we're doing is looking at subatomic particles. So these are particles with really weird names like quarks and muons and leptons, et cetera, bosons. So these are subatomic particles, and these are the things that make up protons and neutrons and electrons. So it turns out that protons are actually made up of smaller particles called quarks. And we've discovered some of these at the Large Hadron Collider. So this is a big circle underneath the ground, like 50 feet under the ground in Switzerland and France, I think. It goes across the country's borders. And it's like 10 miles across, 18 miles in diameter. And they send these little streams of protons around and around and around in this huge tunnel. And then eventually they crash together. And when they crash together, we see what comes out of them, right? Because when you crash two protons together at extremely high speeds, they break into their component parts, and we see what's in there. And then the center where this happens is called CERN. It's like a French name, Centre Européen Recherche Nucléaire. So it's like the European Center for Nuclear Research, or the World Center for Nuclear Research, but we just call it CERN. That's the abbreviation. So the Large Hadron Collider is the actual like smashing stuff together, and CERN is like the office space, the big head place. Okay, so let's take a look at those three videos. I'm going to have you watch them independently, but let me show you where one might find them. So here we are under the mighty atom. And first, I want you to watch this Schrodinger's cat video. So this Schrodinger's cat video is about how something can exist and not exist at the same time. It's in the mighty atom reading about Schrodinger's model. And then go ahead and watch Inside the World's Largest Atom Smasher, the Large Hadron Collider video. That'll explain like what's happening right now with current research in subatomic particles. And then this LHC animation, which is a Large Hadron Collider animation, showing the pathway of these protons as they smash together. Awesome. And then I'll also throw in a video for wave-particle duality that might be helpful. All right. Enjoy that. And hopefully you now have a slightly better understanding of atoms, atomic structure, electrons, and how the world is made up. Enjoy.